Hello class. Today we're going to talk about integrals. Integrals are a mathematical way of summing up a function. They also basically undo a derivative. They have an incredible amount of uses. For instance, if you know how an object's velocity changes over time and calculate the integral of the velocity, you can figure out how far it has traveled. If you know how the net growth rate of an organism changes over time and calculate its integral, you can figure out how the population is changing in time. If you know the rate of new positive coronavirus tests as a function of time and calculate its integral, you can figure out how many people have tested positive for the coronavirus. Integrals are also crucial to differential equation models, which are frequently used to model everything from the global climate to the spread of infectious diseases. They are constantly used in math and science, so we're going to spend this lecture trying to develop an intuitive understanding for what integrals actually mean. All right, before we dive into integrals, let's talk about summation. In mathematics, summation refers to the addition of a sequence of numbers. We often refer to these numbers that we're adding up as sums. We can conduct summations using many different things. We could sum numbers, we could sum functions, we could sum vectors, we could sum matrices. There are also two fundamentally different types of summations. One is the summation of a finite sequence of numbers. This means that we have a finite amount of numbers that we are summing. The other is the summation of an infinite sequence of numbers, which is also referred to as a series. We'll come back to the summation of an infinite sequence of numbers in a moment. But first, let's talk about a summation that is pretty easy for us to understand and particularly important. The summation of the total number of positive tests for the coronavirus in the US. I started by downloading some data on the number of total cases of coronavirus that were reported each day. I've plotted them here. This graph shows the year-day on the x-axis. The year-day is basically the number of days that have passed since January 1st. Beneath the year-day, I've also shown the actual date, since I know that you don't normally think in year-day, you think in calendar days. The data that I was able to download goes up to March 23rd. On the y-axis, I have the number of coronavirus positive tests. I'm going to call it f of n. But note that with this data, f of n is only defined for integer values of n, because the data that I downloaded only has daily information. It's not broken down by the second, minute, or hour. Okay, this is pretty simple data, and I bet that you've seen plots like this in the news already. Since this data is for the number of new positive tests each day, if we want to find out the total number of positive tests, we can just add up all the positive tests that have occurred so far. And for this, we'll use the summation. This equation tells us that the sum from n equals 1 to n equals 84 of f of n equals f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6 plus f of 7 and so on, all the way up to f of 84. So we're just adding up all of the values of f of n from 1 to 84. Of course, f of n is the number of coronavirus positive tests on the nth day. So when we sum f of n from 1 to 84 and find the value 46,442, it tells us that there had been 46,442 positive tests in the US from the beginning of the year until March 23rd. Of course, that's not the only thing we could calculate using a summation. For instance, what if we actually wanted to know the total number of cases during the week leading up to March 23rd? In that case, we'll need to calculate the sum of f of n from n equals 78 to n equals 84. This is, of course, equal to f of 78 plus f of 79 plus f of 80 plus f of 81 plus f of 82 plus f of 83 plus f of 84, which is equal to 41,781 positive tests. So this tells us that there were 41,781 positive tests during the week from March 17th to March 23rd. If we wanted to figure out the number of cases during the prior week, we would want to compute the sum of f of n from n equals 71 to n equals 77. And we'd find that this summation is equal to 3,907, which tells us that there were slightly more than 3,900 cases during the week between the red lines in this graph. If we want to find the number of cases in the previous week, we need to compute the summation from n equals 64 to n equals 70, which we find is equal to 651 positive test cases. All right, obviously this is pretty easy when the sequence that we are summing over is just some list of numbers. Next, let's talk about something a little bit more abstract and try summing over a sequence of numbers defined arithmetically. Let's talk about the summation of 1 divided by 2 to the n, and we'll sum it from n equals 1 to some arbitrary number, which for now we will call x. So we're just summing the numbers 1 over 2 plus 1 over 2 squared, which of course equals 1 over 4, plus 1 over 2 cubed, which of course equals 1 over 8, etc. All right, let's try this out by first just summing from n equals 1 to 2. In that case, we're computing the sum from n equals 1 to 2 of 1 over 2 to the n, which equals 1/2 plus 1/4, which of course equals 3/4. Next, let's take the sum from n equals 1 to 3. In that case, we have 1/2 plus 1/4 plus 1/8, which equals 7/8. Next, we'll sum from n equals 1 to 4, so that is 1/2 plus 1/4 plus 1/8 plus 1/16, which equals 15/16. Okay, pretty simple so far. But what if we wanted to actually find the sum from 1 to infinity? Well, that might seem weird. If we're summing an infinite amount of numbers, you might think that we should eventually get to infinity. But for some series of numbers, including this one, you don't actually get to infinity. Take a look at that pattern we've started. If we sum from n equals 1 to 1, we would just get 1/2. When we summed from n equals 1 to 2, we got 3/4. When we summed from n equals 1 to 3, we got 7/8. When we summed from n equals 1 to 4, we got 15/16. If you're paying attention, each time we add another number, we get half of the way closer to a value of 1. 3/4 is 1/4 away from 1, and 7/8 is 1/8 closer. 7/8 is then 1/8 away from 1, and 15/16 is 1/16 closer. This pattern actually continues forever. So as we take an infinite sum, we move closer and closer to 1. So the sum from n equals 1 to infinity of 1 over 2 to the n equals 1. Okay, let's plot this really quick. The top plot shows n on the x-axis and 1 over 2 to the n on the y-axis. So that is the sequence that we are summing over, and clearly it gets smaller and smaller as we go along. The bottom plot shows the sum of this sequence from 1 to n. So you'll see that it increases over time, but it seems to asymptote towards 1, which is what it means if our summation of the series from 1 to infinity equals 1. Okay, let's switch gears for a moment and let's talk about algae, or more specifically, the algae called Karenia brevis that we first discussed back in Toolbox 7.1. As a reminder, Karenia is the species of algae that causes the huge red tides or harmful algal blooms off of our coast. It can form blooms stretching for miles and miles, and releases a toxin called brevetoxin that leads to massive fish kills, and can even become aerosolized, making it unsafe for humans to be on the beach. Brevetoxin also bioaccumulates into many benthic organisms, including clams and oysters, causing the fisheries that rely on these organisms to be shut down. Because of these major impacts of Karenia on marine organisms and humans who rely on the seashore, my friend Sven Krantz and his grad students spend a lot of time studying Karenia. One of the main things that Sven and his grad students do is culture Karenia and measure their growth rates. In Toolbox 7.1, we talked about the fact that we could compute the instantaneous growth rate of the algae by taking the derivative of the abundance of algae as a function of time. Determining the instantaneous growth rate required that we make very high resolution measurements of the growth rate by connecting the Erlenmeyer flask in which we are growing our Perennia to a flow-through flow cytometer instrument that allows us to make a new abundance measurement every second. This powerful approach, however, allowed us to look at real-time changes in the growth rate and relate it to things like changing nutrient concentrations as the algae used up all the nutrients in the seawater that they are grown in. And when we made those measurements, we were able to get a plot that looks like this. It shows time on the x-axis and the net growth rate of Perennia on the y-axis. Or in other words, it has the derivative of abundance on the y-axis. Note that the units of the y-axis are in thousands of cells per milliliter per day. This graph clearly shows us that the growth rate starts off low, then starts to rapidly grow to a peak of over 150,000 cells per milliliter being added every day, before crashing to very low levels at the end of the 5-week experiment. Now, let's imagine for a moment that we had this same sort of instantaneous growth rate measurement, but we only saved our data once per day. So we've still got the exact same measurements, just much less frequently. Okay, now we've got instantaneous growth rate measurements, just like we had before, but we only have that data with a frequency of one growth rate measurement per day. Remember what each of those measurements means. They mean the growth rate measured precisely at 1 second in time, but only measured once per day. Now, of course, instead of displaying this data as a set of points, we could also display it as a bar chart. Of course, if we display it as a bar chart like this, you should notice that it really looks a lot like the coronavirus data we had earlier in the toolbox. So if we wanted to take this data and estimate the total amount of phytoplankton that have been added, it would make sense that we could approximate it by taking the sum like we did before. This equation tells us that the total number of cells added is approximately equal to the sum from day 1 to day 35 of the net growth rate. In a little bit, I'll explain why this is approximate here, rather than exactly equal. But first, let's make sure to remember that this is the total number of cells added. Of course, if we want to know not the total number of cells added, but instead the total number of cells that are in our culture at the end of the experiment, we also need to know how many cells we started with. We could thus write a new equation stating that the total number of cells equals the initial number of cells that we started off with, plus the sum from I equals 1 to 35 of the net growth rate. This equation tells us the total number of cells that we have at the end of the experiment. On the other hand, if we wanted to compute the total number of cells at any day in our experiment, we could just make a small change in the equation. Instead of taking the summation from I equals 1 to 35, we'll just take the summation from I equals 1 to a variable t, where t is the day on which we want to know the Perennia abundance. Note that the total number of cells is now a function that will be a function of time. If we put different values for t in there, we'll get different answers. Since this is a function of time, let's go ahead and call it f of t. Of course, it makes sense to call it f of t, because f of t is what we were originally calling the abundance of cells. And of course, that's the reason that the growth rate is the derivative of f of t. Okay, now let's go back to the reason that this equation is approximate and not exact. When we're evaluating this function, we're using growth rate measurements that were taken at one instantaneous or near instantaneous period in the day. For instance, maybe the measurements were made at noon. We're then assuming that the growth rates we measured at noon are exact growth rates throughout the day. That's not, however, the reality. The growth rate changes constantly throughout the day. So if we wanted to compute the abundance of cells from the growth rate more accurately, we might measure the growth rate more frequently. Let's say that we chose to measure the instantaneous growth rate twice per day, at midnight and at noon. Let's think about how we need to change that equation for computing f of t if we have these measurements made at noon and midnight. Well, for one thing, we're not going to do our summation from 1 to t anymore. We're going to sum more values. In fact, we are going to have twice as many values since we added one midnight value for every noon value that we had before. But obviously, if we are summing over twice as many values, but we are summing over things that are basically the same magnitude, we're going to get a value that is twice as high. That can't be right. So we need to change what we are summing over as well. And actually this makes sense. Before we were adding up all the growth rates, and our growth rates were measured in per day. So since we had one measurement of growth rate for each day, we could just sum them all. On the other hand, if we still have growth rates that are measured in units of cells per milliliter per day, but we are making those measurements twice per day, then we will need to multiply the growth rate times 1/2 of a day, because each growth rate applies to 1/2 of a day, either noon to midnight or midnight to noon. All right, so let's write out a new equation with the twice per day measurements. We've now got f of t is approximately equal to the initial number of cells plus the sum from I equals 1 to t times 2 of the net growth rate times 1/2. This should make sense because really what we're doing is every half of a day we're adding the growth rate measured at a point during that half of a day multiplied by 1/2 of a day. But of course this is still approximate because even with measurements made at 1/2 of a day, we're still not capturing the true variability. If we wanted to get even more accurate, we could make our measurements more and more frequently. For instance, we could make our instantaneous rate measurements 4 times per day, or 8 times per day. Obviously, the more frequently we make these measurements, the more accurate we'll get. So if we wanted to get perfect accuracy, we could move to measuring this infinite times per day. And if we want to talk about trying to make almost an infinite number of measurements, we can start to use the mathematical language of the limit that we learned about before. So let's write this equation as f of t equals the initial number of cells plus the limit as n approaches infinity of the sum from I equals 1 to t times n of the net growth rate times 1 over n. This is basically the same equation we had before, except that we replaced 2, 4, or 8 with n. And then we stated that this is in the limit as we make n larger and larger so that n approaches infinity. So this is really what we would get as we measure the growth rate with higher and higher frequency. All right, since we're using mathematical formalism here, let's also replace the words net growth rate with our mathematical notation for the growth rate, which can be mathematically written as the derivative of f of t with respect to t evaluated when t equals I over n. Note that here I've also differentiated t, which is the variable we're using to watch how our time series varies smoothly as the growth rate, from t star, which is the time at which we want to calculate the abundance of the cells. So now if we want to compute the abundance of cells after, for instance, 1 week, we would plug in 7 for t star. Okay, let me clean things up a bit. Let's focus on this equation, but let's really quickly write a new equation. We'll define a new function and we'll call it g of t, and we'll say that g of t is equal to df dt. So g of t is just our measured growth rate. We can now rewrite the first equation as f of t equals the initial number of cells plus the limit as n approaches infinity of the sum from I equals 1 to t star times n of g of I over n times 1 over n. Note that the reason we have I over n in the function for g is that we need to evaluate this function basically from something close to 0 all the way up to t star. But we're really plugging in values of I that go from 1 to t star over n. So if we plug in our highest value for I, which is t star times n, into that equation, we'd be evaluating g at t star times n divided by n, which of course is equal to g of t star, which is what we want. In math, the term on the right-hand side of this equation is special. It's actually the integral from x equals 0 to t star of g of x dx. The term circled in blue is what's known as the limit definition of the integral, and it is one way that you can think of the derivative. What the derivative is really doing is summing over a function with infinitesimally small time steps. Another way that you can think of an integral is the summation from I equals 1 to t star over delta x of g of I times delta x if you make delta x really small. What this bottom equation is really doing is summing over boxes with the width of delta x. What the integral does is it makes those boxes smaller and smaller and smaller to make the result more and more accurate. And in the limit, as our delta x approaches 0, we get the integral above, which gives us an accurate answer to the equation f of t star equals the initial number of cells plus the integral from x equals 0 to t star of g of x dx. All right, let's focus on a couple of these equations in particular here, and let's think about what they're telling us. But first, let's go ahead and just plug in for the initial number of cells. We started our experiment with 40,000 cells per milliliter, so let's plug that into the equation. All right, let's focus on a couple of these equations in particular here. Sorry, let's plug that 40,000 cells per milliliter into our equation. G of t is the net growth rate of the phytoplankton at time t. F of t star is the abundance of cells at time t star. But we already know, as stated in the equation for G of t, or as explained in Toolbox 7.1, that the derivative of abundance with respect to time is simply the growth rate. Okay, let's talk about that derivative. We know from our rule for the derivative of a function that is a sum of two other functions that the derivative is equal to the sums of the derivatives of those functions. So that tells us that the derivative of f of t star with respect to t star equals the derivative of 40 with respect to t star plus the derivative of the integral from x equals 0 to t star of g of x dx with respect to t star. Of course, we know that the derivative of a constant is equal to 0, so we can get rid of that term. All right, so that leaves us with the derivative of f of t star dt star equals the derivative with respect to t star of the integral from x equals 0 to t star of g of x dx. But of course, let's look at what df of t star dt star actually is. Remember that t star is just some variable, so we can make use of the fact that if g of t equals df of t dt, then df of t star dt star equals g of t star, so we can replace that in our bottom equation. All right, this tells us that g of t star is the derivative with respect to t of the integral from x equals 0 to t star of g of x dx. G of x is equal to the derivative of its own integral. Next, let's look at one more substitution that we can do really easily. Let's substitute in for g of x in our abundance equation. We can plug in d of x, df dx for g of x. This tells us that f of t star equals 40 plus the integral from x equals 0 to t star of the derivative of f of x with respect to x times dx. So the integral of the derivative is almost equal to the original function. We just have to add in a constant there. So keep these two things in mind. The derivative undoes the integral, and the integral basically undoes the derivative, although we do have to deal with that pesky 40 out front. These are some of the most important facts in calculus. But now that we've introduced a couple key facts about the integral, let's go ahead and actually define the integral. All right, let's talk about some definitions of the integral. We already determined that the integral allows us to determine the abundance of a population of harmful algae at any point in time if we know the population rate of change in time. We also saw that we could define the integral as the antiderivative. The derivative of the integral of f of x will be equal to f of x. The integral of the derivative of f of x will also be equal to f of x, but possibly plus or minus a constant. We can also define the integral as the net area under a curve, or in other words, the net area between a function and 0. This definition is pictographically explained in the figure in the top right of this slide. When you do the integration, if the function is positive, you'll keep adding to the integral as you move to the right. If the function is negative, the integral will actually get smaller or more negative. The integral can also be defined as the sum of a function made over infinitesimally small intervals. This kind of an intuitive way to think This is kind of an intuitive way to think of the integral, and is the way that we approached it earlier thinking about the sums. It is shown pictorially in this animated GIF. Next we have the mathematical notation for an integral. It has the little integral symbol, followed by the function we are integrating over, and then dx, which indicates we are integrating our function over infinitesimally small changes in x. It may seem like it's unnecessary to add this little dx, but it's actually really important, because in the same way that we learned that we can use partial derivatives to take derivatives of functions that have multiple variables, we can also take integrals of functions that have multiple variables. And that little dx tells us that we are integrating over the x variable, while also allowing us to make some specific manipulations of our equation that we may need to use in differential equations. So don't ever leave that dx out of your equations. You would definitely lose points on the exam if you did. Alright, the last definition of the integral is the limit definition of the integral. It's a really mathy definition, like the limit definition of the derivative. It tells us that the integral from x equals a to x equals b of f of x dx is equal to the limit, as n approaches 0, of the sum from I equals 1 to n of delta x times f of x sub I, where delta x equals the limits of our integration divided by n, and x sub I equals a plus delta x times I. Alright, we're going to follow up on these integral definitions and learn how to calculate integrals in our next two toolboxes. But for now, please don't forget to take the mini quiz on Canvas.